This video is a tutorial for system optimization of the Pegasus GC-HRT. Like many instruments, the HRT requires an equilibration and optimization sequence prior to sample collection. The degree in which the instrument must be optimized is dependent on several factors, including the method of analysis, the amount of instrument maintenance performed, the changes in the mass spec parameters, and the status of the filament and detector. This video will discuss the different optimization steps, when to perform each step, and how to review performance reports after optimization. For the Pegasus GC-HRT to function correctly, the electronic components inside it must be allowed to equilibrate. This process, also referred to as system warm-up, must be done at the beginning of each day prior to optimizing the instrument. Conducting a system warm-up also provides an opportunity for the user to determine the status of the instrument. This can be accomplished by monitoring the stability of the fragmentation of perfluorotributylamine, or PFTBA, to check for an air leak and possible contamination. The following is a summary of the system warm-up procedure to be performed each day. Step 1. Check the vacuum. Before operating the system, check the vacuum tab in Diagnostics to confirm that the analyzer vacuum is reading below 5e⁻⁷ millibar. Step 2. Make sure the high voltage is turned on. To turn on high voltage, click on the HV status indicator at the bottom and select Power Up. The ion source parameters can also be downloaded from a method in this window. Once the high voltage is finished powering up, the HV status indicator will be green. Step 3. Load the GC method to be used for sample acquisition and set the ion source temperature accordingly. If these values have not been established, one can use the method shown here. Open the GC chromatogram window and select the GC method. Click the Send GC Method arrow button to transfer the GC method parameters onto the instrument. Step 4. Start the PFTBA high-resolution profile. Profiling will allow the user to monitor the system status. To begin profiling the instrument, you will need to upload a high-resolution MS method that contains a mass range adequate enough to monitor both the presence of a leak and the stability of PFTBA. The recommended mass range to monitor is 15 to 400, but this may be adjusted to satisfy analytical needs. Once a method has been created, enter Diagnostics and access the Profile tab. Select a method using the Browse button and hit Start to begin profiling the instrument. The masses to monitor for a system leak are mass to charge 18, which identifies water, mass to charge 28, or nitrogen, 32, or oxygen, and mass to charge 69, which is the reference peak of PFTBA. If mass to charge 28 and 18 are both below 20% of mass to charge 69, then proceed with the warm-up procedure. If mass to charge 28 is greater than 20,000 height counts, as shown here, a significant leak is present and must be fixed prior to continuing. Failure to fix this leak may result in premature damage to the filament, detector, and possible contamination of the ion source. If mass to charge 18 by itself is above 20% of mass to charge 69, it is unlikely a leak exists, and in this case, continual heating of the source and column should drive the water out of the system over time. If mass to charge 28 is less than 20,000 height counts, but still greater than 20% of mass to charge 69, it is unlikely a leak exists, and instead the instrument might need to be retuned. Run a full optimization sequence, then re-evaluate the profile and see if the peak ratios have improved. Step 5. Review the status log. While PFTBA profiling continues, click on the Status tab within the Diagnostics window to access the system log. The system log records each step taken by the ChromaTOF software. Each of these steps is given a status icon of either blue, which means normal, yellow, a possible concern, or red, a failure. Red and yellow warnings also display in a message bar beneath the menu ribbon. Step 6. Wait for PFTBA to stabilize. The calibration gas, PFTBA, is used during the optimization process to ensure the best possible signal intensity and resolution. Because of this, the signal intensity of PFTBA must be stabilized before optimization. This stabilization can be achieved during the 30-minute warm-up cycle. To check the PFTBA stability during warm-up, minimize the Profiling tab and open a chromatogram window. Change the view to monitor fragment ions 69, 131, and 219. An example of ideal stability for master charge 219 over 30 minutes can be seen here. The trace should be stable for the last 1,000 seconds of the warm-up cycle. If the trace has not yet stabilized, continue allowing the instrument to warm up. Once the Pegasus GC-HRT has been sufficiently warmed up, the user can begin a system optimization sequence. An optimization sequence includes several automatic procedures designed to automatically adjust the various hardware parameters for optimal data acquisition. These sequences include source and analyzer focusing, or SAF, quick focusing, gain optimization, detector measurement, acquisition processing optimization, or APO, and mask calibration. Source and analyzer focusing, or SAF, should be performed daily and will automatically adjust voltages in the ion source, ion interface, and mass analyzer to reach the maximum response for signal while still meeting the minimum resolution requirements. When the SAF begins, a window is generated displaying the various stages of optimization with a description of which elements are being adjusted during each stage of optimization. Once the SAF has finished, the acquisition processing optimization and mass calibration steps must be run before continuing to sample acquisition. A quick focus can be periodically performed during prolonged data acquisition runs in order to keep the source and ion optics at optimum performance and counteract any gradual drifts. A quick focus can be thought of as a stripped-down SAF. Due to its simplicity, a quick focus procedure is expected to complete in less than 15 minutes. Once the quick focus has finished, acquisition processing optimization and mass calibration steps must still be run before continuing to sample acquisition. A gain optimization, or GO, is designed to find the minimum detector setting that yields good isotopic ratios for low-intensity ions in order to compensate for the aging of the detector. Additionally, the gain optimization determines the detector response for a single ion. This information is critically important to the automatic data filter and compression routines. Once performed, the gain optimization sets the detector voltage globally for the instrument, automatically updating all operational mass spec methods. The gain optimization will need to be performed in high resolution and ultra high resolution modes for both electron impact and chemical ionization methods. The gain optimization does not need to be run daily, but needs to be rerun from time to time as the detector ages. Once the gain optimization has finished, acquisition processing optimization and mass calibration steps must be run before continuing to sample acquisition. A detector measurement, or DM, is automatically run during the gain optimization when a relative detector voltage offset exists in the current MS method. The detector measurement updates the system's expectations of the response from a single ion. The detector measurement does not change the global detector voltage set by the gain optimization. It only updates the system response at a given RDV offset. A detector measurement should be run independently of a GO anytime the RDV offset is changed within an MS method or if a different MS method with a non-zero voltage offset is used. The Acquisition Processing Optimization, or APO, collects profile data of PFTBA and generates statistical models of peak shapes through the mass-to-charge collection range. This information allows the KDAS to efficiently convert and condense sample data in real time. Once the APO has finished, a mass calibration must be run before continuing to sample acquisition. The mass calibration derives an equation for converting between time of flight and mass to charge and saves coefficients to the MS method. The mass calibration is performed based on parameters entered into the mass calibration table within the MS method. The mass calibration coefficients can be applied to any previously collected data by using a data processing method as needed. Mass calibration involves complex processing procedures that are covered in detail in a mass calibration video. The tune validation step collects a small amount of data which will be displayed in the performance report and should be performed after every optimization procedure. The performance report evaluates the tune validation data to determine if the system is ready for sample acquisition. This report produces a status that determines whether analysis should continue or if the instrument requires further attention to achieve optimal performance. It also contains data that can be used to troubleshoot potential problems within the instrument. Depending on the status of the instrument and the acquisition methods, the following optimization sequences may be used. A full optimization procedure should be used in the following scenarios. After system maintenance, whenever there is a break in the analyzer vacuum, whenever there is a modification of the mass spectrometer method, the source parameters, the tune parameters, etc., if there is a change in the carrier gas flow rate or composition, whenever the filaments are switched, or if the instrument has been idle for an extended period. The full optimization consists of a source and analyzer focus, gain optimization, APO, and mass cal, in that order. If the user is continuing to use the same unchanged mass spec and GC methods for sample analysis, then a daily optimization schedule can be used. The detector voltage should not change daily, but needs to be rerun from time to time as the detector ages. The daily optimization sequence includes an SAF, an APO, and a mass cal. During a long sequence, a quick focus should be periodically performed to keep the source and ion optics near optimum and counteract any gradual performance drifts. An optimization during a sequence includes a quick focus, APO, and mass cal to quickly advance to sample collection. To run a system optimization, select the Acquisition Queue tab and begin building an acquisition batch. Each optimization step can be added by creating a line item and manually selecting an option in the Type drop-down menu. Be sure to add a GC and MS method to each step of the queue. The optimization sequence will create a global tune, so it is important to select the GC and MS methods that will be used for sample collection in order to allow the system to account for any changes caused by gas flow and temperature settings in the methods. After an optimization procedure has been chosen and the acquisition queue has been created, click the play button to proceed with optimization. If an SAF is included in the optimization, the auto-tune window will appear listing each step of the SAF. As the steps of the tune complete, they will leave the queue and a data file will be generated that can be reviewed manually in the Acquired Samples tab. Once the optimization procedure has finished, the performance report is ready to be reviewed. To access the performance report, go to the System tab and click on the Performance Report button. This will bring up a list of the most recent reports. Select the desired report and select the Display Report button to open a report in a pop-up XPS window. These tune performance reports are full of valuable information displayed in the following sections. The acquisition information lists the user, instrument, date and time, GC method, and mass spec method used while acquiring data for the tune performance report. The tune information lists the current optimizations associated with the mass spec method. These optimizations include the source and analyzer focus, gain optimization, acquisition processing optimization, and mass calibration. A status icon in the upper right corner displays whether the tune performance criteria have been met. A green checkmark with the status pass indicates that all of the tune criteria have been met. A red handprint with the status fail indicates that one or more of the tune criteria have not been met. Recommended actions to improve the system will be listed below in the summary. The action will advise the user on how to improve system performance. The instrument parameters section lists the instrument conditions while running the tune validation. These instrument conditions include the source temperature, active filament, detector voltage, analyzer pressure, transfer line temperature, GC oven temperature, and carrier gas flow from the GC. The summary section contains recommended actions based on the current system status. The criteria include the intensity and resolution of mass to charge 219, the RMS mass accuracy in ppm, and the ratios of air and water to meet minimum leak check requirements. The summary section also provides data used for the report along with other data which can be used for comparison or to troubleshoot problems with the instrument. The data from the mass to charge 219 peak from the PFTBA analyzed during tune validation is displayed in the optimization table. The table lists the observed mass, intensity, resolution mode, mass to charge 219 mass accuracy, and RMS mass accuracy. The criteria for the maximum amount of air allowed in the instrument is displayed in the leak check table. The data for these peaks is listed later in the summary section. Different HRT instrument models might use different air-water criteria than shown here. The profile plot of mass to charge 219 gathered from the latest APO performed on this mass spec method is displayed so that the user may visually check for excessive tailing, asymmetry, or skew which may have occurred during optimization. The calibration table is a portion of the calibration matrix which shows the expected masses and mass accuracy from the PFTBA analyzed during tune validation. It also shows the results from the last tune validation run prior to this analysis for comparison. The mass accuracy RMS is the mass accuracy calculated based on the masses listed in the mass calibration table in the MS method. The isotopic pattern table is a representation of the proper fragmentation patterns of PFTBA analyzed during the tune validation. The table calculates the ratio between the C12 and C13 and compares it to the expected values based on the known abundance of C12 to C13. The informational table shows the resolution, intensity, and percentage for specific air, water, and PFTBA fragment ions analyzed in this tune validation. It also shows the results from the last tune validation for comparison. The spectrum from the tune validation is displayed to visually show the air, water, PFTBA fragmentation, potential contaminants, and any other ionization fragments which may have occurred during analysis. After the system has been warmed up and the tune report has been reviewed, the system is ready to be run. Be sure to periodically maintain the performance of the instrument with a quick focus optimization procedure as needed. Keep in mind that any time the GC or mass spec methods are changed, the instrument will need to be fully optimized to adjust for any changes caused by these new settings. The instrument should always be placed into a standby mode if left idle for more than 1 hour. By default, the filament voltage does not shut off after profiling, so enabling the ion source standby will greatly preserve the life of the detector and the filaments. To set up a standby procedure, go to the Diagnostics window and select Standby. Check the Automatically Go to Standby box and enter the desired time frame. Specific settings can be changed in the table below. LECO's recommended standby settings for each source type are provided as default settings. The GC standby method is optional and can be used to preserve the carrier gas. To enable a GC standby method, first create a GC method with the following settings. In the Standby window, check the GC method box and use the Browse button to select the newly created Standby GC method. This concludes the video on system optimization for the Pegasus HRT. Additional information can be found in the ChromaTOF manual and in the HRT operational guide.